In today's talk, I'd like to go over issues about confounding and variable selection. Okay? And you've already learned this before, so part of it's a review, but I'm going to try to focus on some practical aspects. Okay? And the practical aspects comes in the following way. Okay? So you've learned how to use DAGs, which is good because by using DAGs, you can figure out that some variables really aren't a confounder. You can figure out that some variables are mediators, that some variables, if you controlled for them, you might open up a collider path and increase confounding instead of making it less, and all of those things. So I want you to remember that and start off with that. Now, once you've done that, unfortunately, we have these big cohort studies where we measure hundreds of variables about people. Let's take the Framingham study, a very famous cardiovascular cohort, right? They have an awful lot of information, hundreds and hundreds of variables. And it's been going since 1948. They've actually studied a lot which of these variables might be predictors of, for example, blood pressure. You go to the Framingham study, you say, well, I want to look at this other variable as a potential predictor of blood pressure, and they're going to say to you, well, here are all the things we know are predictors of blood pressure, so you should put that in your model. Wrong. That's not true. First of all, some of them might be mediators for your exposure. Some of them might be colliders, and controlling for them makes things worse. But most importantly, controlling for confounding has nothing to do with what are predictors of the outcome. It's about what are predictors of the exposure. Now, we'd also like them to be predictors of the outcome, or we don't care about them, but primarily you're focusing on what's a predictor of your exposure that might also be a predictor of the outcome. And that's because in a randomized trial, the people who get the treatment and the people who get the placebo have the same distribution of age and body mass index and all these other things by randomization. And we're trying to mimic that. So we're trying to make the exposure balanced with respect to these other variables. We're not trying to fit the best possible model to predict blood pressure. That's for people who do predictions. You're testing hypotheses. Okay? So we have all these variables. We have a lot of them. And we need to decide which ones to put in the model. So lesson number one, we're focusing on the exposure, not on the outcome. We need to think about whether any of the variables that might be associated with exposure might be associated in a way where we don't want to control for them. And that's what that's about. Okay? Unfortunately, that's still going to leave you with a lot of possible variables, right? And so you need some pragmatic way to choose among them. So the goal, remember, is to make the exposure independent of these variables, which are also predictors of the outcome. Now, obviously, if the exposure is related to a variable that isn't a predictor of the outcome, that's fine, right? Okay, but we still need to do some selection. So there are various approaches that are out there. Now, one that you've undoubtedly heard about is what I call the 10% solution. The 10% solution basically says, I put this variable in the model predicting the outcome. If the coefficient of my exposure changes by 10% or more, I leave it in, otherwise I can take it out. So first of all, that's not really saying a lot about the relationship between the exposure and this variable, other than they're clearly related or the coefficient wouldn't change, we think. I'll come back to that. But what if I have 100 variables that each change the coefficient by 9%? I leave them all out. I could have tremendous confounding, and I'm not capturing it with this. Not only that, let's, we often talk about what will happen, asymptotically. Do I get the right answer? Is the size of my study population gets bigger and bigger and bigger? Do I approach the right answer? And the answer is no, right? This approach does not have asymptotic properties. If I have twice as many people in my study, that changes the p-values for everything, but it doesn't change the percent by which, on average, I expect this covariate to change the slope of my exposure. It's still only 9%. I still leave it out. So this approach doesn't get better as the sample size gets large. That's not so good. Historically, stepwise regression has been very popular, and in fact, if you open up the American Journal of Epidemiology and various other, medical journals, you will see stepwise regression is used a lot. I have all these variables, I put them in, and, I take the ones that are significant. Now think about that, right? What we're trying to do is balance the distribution between exposure and covariate so that the low exposed people and the high exposed people have roughly the same distribution of this potential confounder, right? What does that have to do with the p-value of the confounder as a predictor of the outcome? Well, in principle, nothing, right? On the other hand, I only care about equalizing the distribution for variables that do predict the outcome, so I care some about the p-value, but it's not so strong, right? However, which variables make it in are highly sensitive to the order in which you consider them. Are you doing backward selection, forward and backwards, various other kinds? But the problem is all of these things wind up adding or subtracting one variable at a time with some other covariates in there, but not necessarily all of them, and asking whether to keep them or not. And so random variations in particular values of the covariates in different people will determine which ones get kept and which ones don't get kept. If these 4 covariates are in first, I will keep this one. If a different 4 come in first, I won't keep this one. It's not very good. So here's something that is decently good. It is the Lasso. It was developed by Rob Tibshirani, who's a statistician and a very good one. And it actually does have asymptotic properties. in the limit, as your sample size gets big, it tends to only choose variables that are predictive of your outcome. Now, they doesn't mean that they're confounders, right? You might already have your exposure be equally distributed among, your confounder equally distributed among people with low exposure and people with high exposure, and so you don't need to control for it. But at least you're not controlling for things that happen to, in your sample, be correlated with the outcome, but barely, but really aren't significant predictors, because it tends to select the ones that matter. And the way it does that is as follows. Least squares regression says that we want to find the slope, remember, that minimizes the sum of the squares of the error. So I get a line that goes through the middle. So that's the first thing that I want to do, and usually that's it. But with the lasso, what Rav Tibshrani said is, aha, we're going to impose a constraint, okay? We're going to basically say, you only have so much to spend on coefficients, right? The sum of the absolute value of your coefficients has to be less than 23, right? So that means that if I make coefficient B1 bigger, I might have to make another coefficient B11 smaller in order to stay within my budget constraint for the total amount of coefficient that I can spend. Now, the difference between this and stepwise regression is the following. With this budget constraint, I might find that, gee, x2 is a really important predictor of my outcome. I don't want to constrain that coefficient at all. I want that coefficient to be the one I would get if I just minimized the sum of squared errors. And that means that to stay in my budget constraint, I'm going to set the coefficient of x6 to 0. Well, if a coefficient is 0, that means basically that variable isn't in the model. So this is a form of variable selection. When you run the lasso, various variables are going to get dropped out of the model. They're going to have coefficients of 0, because doing so allows you not to shrink the coefficients of the important predictors. So that's sort of what you want, and it has a great advantage over stepwise regression, which is all the variables are in there at the same time, and this shrinkage is not dependent on which variables have entered already or dropped out already or things like that. They're all happening at once, considering all the other variables. I'm going to meet my budget constraint by making U 0. Sorry, nothing personal. You just don't predict this outcome. So that's the basic idea of the lasso. That's how it works. And, of course, the issue is, how do I choose t? Well, if t is 0, then all the coefficients are 0. I have nothing in my model. If t is bigger than the sum of the absolute values of all the coefficients you would get from least squared regression, then they're all in the model, and I haven't selected anything. So I'm going to try to make t be some number between those 2 points, so I select some variables. How do I choose t? By cross-validation. So what do I mean by that? Tenfold cross-validation is what's typically done. It's a good way to do this. I take my data set and I divide it into 10 chunks of equal size. The first 10%, the second 10%, up to the last 10%. Just randomly group people into 10 groups, okay? Now, take a value of t out of the air. Put it into that, put it in there, right? So now I'm going to squeeze the bees. Do that with groups 2 through 10. So 90% of the data, I fit the model, I get my bees, I get my coefficients out of it, right? So now I have a model, I've dropped some variables, I have coefficients for the variables that I didn't drop, and so I can, for these 10% of people who weren't used in fitting the model, I can predict, given their values of the independent variables of the covariates, what their blood pressure would be. And I have their measured blood pressure, right? And so I can calculate the sum of the squared prediction error, the difference between what their real value was and what the predictions said. Because what I'm trying to do is choose variables that are good predictors of my outcome. And I'd have to test that in data that wasn't used to fit the model, to find out if it really predicts the outcome well. So I do that. And I save those sum of squared errors. I'm going to stick them right there. And then I put these people back in, and I drop the second group out. And I do the same thing. I fit the model using the same t. I get some coefficients. I predict for the left out sample. Of course, I predict with some errors. I calculate the sum of squared errors in that left out data. And then I cycle through all 10. And I add it up. And that's the sum of squared errors I get in validation data for that choice of t. Now I go back and I choose a different t. And I get a different sum of squared errors, right? And so which value of t do I pick? I want to pick the value of t that gives me the best possible fit, the best possible prediction in a validation data set. So I want to pick the value of t that makes that the smallest. Now the other thing I want is I want the computer to do this for me and not having to do it by hand, right? And fortunately, that's true. Okay, so doing that chooses a value of t, which effectively means chooses which values, which variables to leave out and which to keep in. That gives you the best possible prediction in a validation data set. And in the limit, as the sample size gets large, this gets better and better at picking out the right variables that give you the best possible prediction, which means those variables really are predictors of the outcome. Now, they still may or may not be confounders, but at least I'm worrying about confounding only for variables that might predict the outcome. Okay? So that's the basic idea of the lasso. Now, there are alternative ways to pick the parameter t, including something called Akaiki's information criterion, the Bayesian information criterion, bias-corrected Akaiki's information criterion, etc. All of them asymptotically, that is to say, as sample size gets big, approach the results from cross-validation. But the software that we have will do all of these, actually. I recommend cross-validation. I think that's, the best way to go here. But any of them is reasonable. So The key advantages of this is, first of all, I get rid of the problem that the answer depends on the order in which variables enter or leave your stepwise regression. So it selects variables to include, but does it with all the variables being considered at once. And it has these asymptotics. It will, in the limit as the sample size gets big, select the right variables and only the right variables. Most of the time and all the time if you do the following variation, which is called the adaptive lasso. So the adaptive lasso says, look, you've got this budget, right? You're going to spend only 23. Some of the coefficients got to be less than 23, right? But when you're allocating that, it would be nice to have some initial idea of which are the important variables. That might help you allocate those 23 units of coefficient more effectively. And so what you do is you fit the regression model with all of the variables in there, controlling for everything you've measured. That gives you kind of noisy estimates because you've probably measured a lot, but you get a coefficient for each one of the variables, right? If you standardize your variables so they all have the same scale, then the ones with the bigger coefficients are the ones that even in this very crude throw everything in at once model look more important. If I divide then every variable by 1 over its coefficient, then what I wind up as my constraint is not that the coefficient for each variable is being constrained, but the ratio of that to its starting point when I considered everything. So if this was big because variable I is very important, then I can spend more on variable I can make BI bigger without making the ratio too big. And so it helps the model say, yes, spend more of your T units of coefficient on variable I because it's really important. And if you do that, then asymptotically, this which is also built into SAS, this model will select only the variables that are important and all of the variables that are true predictors of our outcome. And that is a pretty good deal. Now we still have to worry about, are these variables correlated with exposure or not? And if they're not, maybe you don't want to put them in, maybe you do, and that actually will depend on what kind of regression we're fitting, and we'll talk about that a little later. So that wraps up this discussion about variable selection, and we'll try to do some variable selection in class. Thank you.